But all right, and that's of A. And this was the velocity of A. And this was prior. So if you see a 1 subscript, it's prior. Okay, so then post-collision, I'm going to draw them up here. So it's going to go bam, 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 explosion, and then go that way. And then that one is going to be shot down this way. And this angle is given of 30 degrees. Okay, and then that angle also is 30 degrees alpha. So first thing we should notice is that there's no horizontal X or Y external forces, right? They didn't mention any type of external forces. So we can say that the momentum is conserved. Okay, so then what we need to do is say, once we establish that, is the momentum before equals the momentum after. So we need to look just in the X direction because at first only X direction motion occurs. And we're going to have the momentum of A. Was that moving in the X direction to begin with? Yes, it was. It was going to the right at a velocity of 2 meters per second. Right? So we know that the momentum of A1 is just the mass of A times the velocity of A, and the 1 means before the collision.
Okay.
And then the B1, which is the momentum of B prior to the collision, and both of these technically are X momentums, would be 0 because it's at rest. Are we okay so far? You're okay so far?
Yes, it'd be 0 because the velocity is 0, so then 0 times the mass would make it still 0.
Okay. All right. So now after, what's going on? Well, after we have to look at the different scenarios. So we're going to have the mass of A times the velocity of A in the X direction after the collision. So this is the X direction, and the 2 means after the collision.
Okay.
Okay. And we also have a momentum of B, move a little bit to the right, of B with the velocity of B in the X direction post-collision. So what is different here? We have to account for the angle, right? So the velocity given to us. All right, so here we have, let's start plugging and checking. We know that the mass is
20.
And the velocity was 2. And then that's going to equal the mass, which is 20. Now, what is the velocity of A after the collision in the X direction? How do you think we would find that out?
Oh, sorry, I have the adjacent and I want the hypotenuse.
Okay.
Well, I have the hypotenuse and I want the adjacent.
Exactly. You have the hypotenuse and you want the adjacent. So how do you deal with that? This is 1.0 meters per second, which is V, and I want V sub X.
Cosine theta?
Sure. So if I do cosine of theta, which is 30 degrees, I get the X component over the velocity. So then now I just figured out what the X component of my velocity is.
Okay.
Now I can plug that in to right here. And then mass of B was 12 kilograms, and we're looking for VBX2. Now it's just plugging and chugging. Okay, and when you do all that, you should get VBX2 is 1.89 meters per second. Okay, are we done is the question.
What?
Are we done is the question.
What the velocity of the final velocity of B or which velocity of B? Well, I'm assuming, yeah. So, yeah, are we at the final velocity of B?
It's part of the final velocity of B. It contributes to the final velocity of B.
Because I know there's the whole Y direction thing.
Yeah, right. Because right now what we did just purely the X direction. So this is V sub X. And I told you for a vector, we need V sub X comma V sub Y, right?
Okay.
So let's do the same thing, but just purely in the Y direction. All right. So if we did the Y direction, what is the momentum before for A?
Can you repeat the question?
Sure. What is the momentum of object A prior to the collision? In the Y direction.
Prior to the collision?
Yeah.
0?
0. Good. What is the momentum of object B, robot B, prior to the collision? In the Y
0?
direction. Good. And then since it's conserved, it equals the momentum after. So the momentum of A after the collision, momentum of B after the collision, and we are actually doing purely Y's here. Okay. So what is the momentum of A after the collision in the Y direction?
Sine.
Good. So you got M sub A, V sub Y, but then that becomes AM sub A, and this is V sub Y, AY. And so it's the velocity of A after the collision in the Y direction. Right? So then we can replace that with the velocity of A after the collision times the sine of theta, which was 30 degrees. Are you okay with all that?
Yeah.
All right. So then we have to come up with the same thing for B. So that would be plus the momentum mass of B, velocity of B to Y, but we don't know anything about that. So all we can do is just plug and chug from here. So we got 0 equals sine of 30 we know is, I apologize about that. So your answer should still be that. What's that?
On the problem right now, don't we know M of B? Isn't it still just the original mass?
Yes, that is correct. So that's 20 kilograms, and that would be UB2Y. And then on this side, we have the 20 kilograms. Velocity of A was 1 meter per second, and then the sine of 30 is 1/2.
Okay.
So then if you subtract that over, you're going to get a negative 10, and then divided by 12, that will give you UB2Y. And your units are going to be meters per second when you're done. And it will give you a negative 0.83 meters per second. Are you with me?
Yeah. So now I have my velocity in the vector format thing.
Good. Now, exactly, we know that V is going to be VB2 is going to be equal to the x component comma the y component. And then how do I get the actual velocity? This is the velocity vector. How do I find the actual velocity?
That I don't know.
You find the magnitude. So V, no, the magnitude is take the x component squared and the y component squared, add them together, and square root it. That's the magnitude. So then negative 0.83 meters per second. And then when you do that and combine them, you're going to get 2.1 meters per second. You understand how I did that?